We'll start in about 1 minute. Today we'll finish section 10.1 on curves defined by parametric equations, and we'll get started in section 10.2, which is calculus with parametric curves. For a couple of minutes, we'll look at the problem that we were working on at the end of the class yesterday. So there's two ways you can eliminate the variable. If you square x, square both sides of this, you get x squared equals t minus 2. And so x squared plus 2 equals t. And then in the other equation, replace t with x squared plus 2, so you get y equals 3 times x squared plus 2 minus 2. And simplify that, you get y equals 3x squared plus 6 minus 2, or y equals 3x squared plus 4. And we observe from how the equations are defined, x is the positive square root of t minus 2. So the x values must be greater than or equal to 0. And as we saw yesterday, the graph will just be a half of a parabola with the vertex at 0, 4. So that's the graph that we get. But the other way that we did it yesterday is also fine if you solve y equals 3t minus 2 for t, and then substitute t into the other equation. So when we add 2 and divide by 3, we get t equals y plus 2 divided by 3. And then in the other equation, replace t with y plus 2 over 3. So we get the square root of y plus 2 over 3 minus 2. And you can simplify a little bit to get the square root of y minus 4 over 3. So you can also graph this if you remember how to graph square roots. So we get the same graph either way. Okay, we'll move on to the last part that we're going to cover in 10.1, which is finding parametric equations for a cycloid. Okay, a cycloid is a curve traced out by a point P on the circumference of a circle as the circle rolls along a straight line. So we'll suppose a circle with radius r rolls along the x-axis in the positive direction with the initial position of point P is at the origin, and then find the parametric equations for the cycloid. Okay, so we're starting out in the xy plane with a circle of radius r. So pretend like that's a circle. Our point P is at the origin. And we're going to roll it to the right. So when it's rolled to the right a little ways, our point P will be, let's just say, right about there. I might draw this circle a little bigger than the one on the left. So we get something like this. And the radius is r. And we'll suppose that we rolled through an angle of theta degrees. Not degrees, theta radians. So what we want to do is find the x and y coordinates of the point P. So the distance from the y-axis to this point is the equivalent to the x-coordinate of that point. And the distance from this point to the y-axis is equal to the y-coordinate of that point. Okay, this distance down here along the x-axis, this is the same as the arc length of this part of the circle. And since the central angle is theta and the radius is r, the arc length is r times theta. So the distance from the origin to this point is the same as the arc length because that's what was rolled through. So r theta is that length. And we're going to take a look at the right triangle that is formed using the angle theta. So let's look at a bigger version of that. So the radius is r, that's the hypotenuse. This angle is theta. And then the opposite side of theta is here, and the adjacent side is there. So we'll come back to this right triangle in a couple of minutes. But notice what we have. If we add x to the length of the opposite side of that triangle, that's going to be equal to r theta. So we can write x plus the opposite side of this right triangle is equal to r theta. And then for the y-coordinate, we can say if we take y and add the adjacent side of that right triangle, that's equal to the radius r. So are we all in agreement about that? It's pretty basic geometry. And we'll also use a little bit of trigonometry. So in terms of theta and r, we'll find both the adjacent side and the opposite side. So how are we going to do that? So if I take the sine of theta, just by definition, the sine of theta is equal to the length of the opposite side divided by the hypotenuse. So this is the opposite side divided by r. We want to know what the opposite side is, so the opposite side is r times sine of theta. And then the cosine of that angle, theta, by definition, that's the adjacent side divided by the hypotenuse, which is length r. And so the adjacent side is r times cosine of theta. Okay, so now we're just a couple of steps away of parameterizing the point P on the cycloid. Okay, so since x plus the opposite side equals r theta, we can write x plus r times sine of theta is equal to r theta. And so when we solve for x, we just subtract r times sine theta. So the parametric equation for x is r times theta minus r times sine of theta. And then the other equation, y plus the adjacent side, but the adjacent side is r times cosine theta. And that's equal to r. So the parametric equation for y is r minus r times cosine of theta. So you'll sometimes see both of those written in factored form. So for x, instead of r times theta minus r times sine of theta, we can write it as r times the quantity theta minus sine of theta. And the same goes for y. Instead of r minus r times cosine theta, we can write y as r times the quantity 1 minus cosine of theta. So the authors of the textbook seem to like problems involving this cycloid. So when you're reading through the sections, then at least, and it also explains in the book how to find those parametric equations. Okay, we'll move on to section 10.2 for now. Okay, in section 10.2, we'll learn how to apply calculus to the parametric curves. Okay, so applying calculus to parametric curves enables us to solve problems involving tangents, areas, arc lengths, and surface area. So we'll start with tangents. So we're going to suppose y is a differentiable function of x with differentiable functions f and g used to define the parametric curve x equals f of t and y equals g of t. So note, not only is y a function of x, but y is a function of t. So when we apply the chain rule, the derivative of y with respect to t is equal to the derivative of y with respect to x times the derivative of x with respect to t. And if the derivative of x with respect to t is not equal to 0, then the derivative of y with respect to x is the derivative of y with respect to t divided by the derivative of x with respect to t, or g prime of t divided by f prime of t. So this is how to define the derivative of y with respect to x when both x and y are defined with parametric equations. Okay, so by using the formula above, we can find the slope of a tangent line to a parametric curve without eliminating the parameter t. So we can also address concavity questions by analyzing the second derivative of y with respect to x. And this might all look kind of complicated at first, but it's not so bad if you read through it a few times. So we can find the second derivative of y with respect to x if we replace y with dy dx in the equation that we see above. So this is the equation that we saw above for the derivative of y with respect to x. It's equal to dy dt over dx dt. To find the second derivative, just replace y with dy dx. So the derivative of y with respect to x is in the numerator the derivative of y with the derivative with respect to t of dy dx over dx dt. So when you've done this a few times, it starts to click. It'll make more sense. Okay, let's do this example where we find an equation of a tangent line to a parametric curve where x is equal to t to the second minus t, and y is equal to 1 plus 2t to the second, corresponding to t equals 2. Okay, so to find an equation of a tangent line to a point on the curve, well, we need to know where the point is. So we need an ordered pair. And then we need to know the slope of the tangent line. And then once we know a point on the curve and the slope of the tangent line through that point, then we can write down the equation for that tangent line. So let's find the point first. Well, the point corresponds to the t-value 2. So when t equals 2, x is 2 to the second minus 2, or 2. And the y-coordinate is 1 plus 2 times 2 to the second. So that means y is 9. Okay, so that is the ordered pair of the point on the curve through which a tangent line will pass, and we want to find the equation of that tangent line. So that is the point on the curve. Now we want to find the slope of that tangent line that passes through that point, 2, 9. So if we can find the derivative of y with respect to x, and then evaluate the derivative when x equals 2, then we'll know what the slope of that line is. Okay, but we're going to use our derivative formula up here. The derivative of y with respect to x is the derivative of y with respect to t divided by the derivative of x with respect to t. Okay, so for the numerator, since y equals 1 plus 2t to the second, the derivative of y with respect to t is 4t. And in the denominator, the derivative of x with respect to t, since x is equal to t to the second minus 2, the derivative of x with respect to t is 2t minus 1. And then the slope of the tangent line will be found for t equals 2. So when t equals 2, the slope of the line tangent to the curve, replace t with 2 in the derivative, we get 8 divided by 3. So the slope of the line is 8/3. Okay, so now we have our slope and we have the point. So the tangent line equation we can just write the point slope form. We can write y minus 9 equals the slope 8/3 times the quantity x minus 2. So that's a good enough equation if you want to leave it in that form. Okay, the second part of this, find the t-values where the curve is concave up. So in terms of derivatives, what does that mean? Yeah, if the second derivative is positive on an interval, the graph is concave up. So we want to find the second derivative in terms of t, and then determine for which values of t the second derivative is positive. Okay, so here's our second derivative formula up here. So we already know what dy dx is. Dy dx is 4t over 2t minus 1. So our second derivative, to move this up a little bit, I guess. So the second derivative of y with respect to x, according to this formula, we're going to compute the derivative with respect to t of what dy dx is. But here's our dy dx, so I'll just write it the 4t over 2t minus 1. And the denominator is the derivative of x with respect to t, which we already found to be 2t minus 1. Then when we're finished computing the derivative, we'll replace t with, well, actually, no, we'll determine which values of t the second derivative is positive. Okay, so in the numerator, we have to apply the quotient rule to find the derivative of 4t over 2t minus 1. So for now, the denominator stays the same, 2t minus 1. And then the derivative of 4t over 2t minus 1 with respect to t. So we get 4 times 2t minus 1 minus 4t times 2 divided by the denominator squared. So we can write this as a single rational expression. The denominator is going to become 2t minus 1 to the third. And then we'll simplify the numerator. So 4 times the quantity 2t minus 1 is 8t minus 4. And then minus 8t. And we're just left with negative 4 over the binomial 2t minus 1 to the third. Okay, so there's one value of t where this expression is undefined. It's when t is equal to 1/2. So on one side of t equals 1/2, on one side the second derivative is going to be positive, and on the other side it's going to be negative. So we can pick, this is our t-axis, we can pick a test point. We can pick t to be 0, and when we replace t with 0, we get negative 4 over negative 1, which is positive. So t less than 1/2 corresponds to the second derivative being positive. If you want to make sure that you can check the other side also, if you pick x to be, or t to be 1, then 2t minus 1 is 2 times 1 minus 1 is just 1, and we get a negative number. So yeah, the second derivative is positive when t is less than 1/2. So in other words, the curve is concave up when the values of t are less than 1/2. Okay, let's move on to areas next. Okay, one thing we already know, if capital F of x is greater than or equal to 0 for values of x from a to b, then the area below the graph of f and above the x-axis on the interval from a to b is just the definite integral of f of x dx from a to b. Okay, if the graph of f for values of x between a and b is traced out once by parametric equations x equals f of t, lowercase f of t, and y equals g of t for values of t between alpha and beta, then the definite integral of f of x dx from a to b is equal to the definite integral of g of t times f prime of t dt from alpha to beta. So I'll just give a basic explanation. You can also do a little bit more in-depth explanation if you look at how we came up with the definite integral in the first place by constructing rectangles, partitioning the interval from a to b into subintervals, and then constructing rectangles and using areas of rectangles. That also works, but I'll just give you a basic explanation. So f of x is a y value, so y equals capital F of x, not to be confused with lowercase f. So y equals f of x, but y also equals g of t. X equals lowercase f of t, which implies that dx is equal to f prime of t dt. And since x is equal to lowercase f of t, we can say that when x is equal to a, since the parametric curves trace out the function capital F, we can say that when x equals a, t is equal to alpha or beta, one or the other. And when x equals b, t is equal to beta or alpha. So if we just substitute into this definite integral, the limits are from alpha to beta. F of x is replaced by g of t. dx is replaced by f prime of t dt. But as you will experience if you do enough practice, there will be some cases where a curve is traced out in the reverse order that you might expect. And in those cases, the integral will be from beta to alpha of g of t f prime of t dt. So don't be alarmed if that happens. Just go with the flow. Okay, so let's find the area enclosed by the x-axis and the curve x equals t to the third plus 1 and y equals 2t minus t to the second. So I'll let you ponder this for a couple of minutes. So a hint is in the statement itself. Find the area enclosed by the x-axis and the curve x equals t to the third plus 1 and y equals 2t minus t to the second. We're assuming that the curve is expressed or can be expressed as a function of x. That is, the curve y expressed as a function of x. So what do you know about integrals that you've already learned how to evaluate for enclosed areas that are enclosed by the x-axis and the curve? So let's just draw a little picture. So if you have the graph of a function of x, and if a region is enclosed by the graph and the x-axis, you might have something that looks like that. So how would we determine what the limits of integration are? So if we want to find the enclosed area between the graph and the x-axis. Well, if we can find this point and this point, if we're just going to graph a function of x with respect to x and integrate it to find the area, we would need to know this x value and that x value. But those two values, or those 2 points, are x-intercepts. And what's true about every x-intercept? Yeah, y equals 0. So at those 2 points, y is equal to 0. So that is going to be a hint. Well, if we want to find the area enclosed by the x-axis and the curve, we want to know the t values where y is 0. That is going to determine the limits of the integral of the parametric curve. See what I mean? So note that y is equal to 0 when 2t minus t squared in factored form, t times 2 minus t is 0. Or when t equals 0 and t equals 2. Okay, so when we use our integral formula up here, the limits of the integral with respect to t are t equals 0 and t equals 2. Okay, so x is our f of t, which is t to the third plus 1. And y is our g of t, which is 2t minus t to the second. And we're using, for values of t between 0 and 2. So we're using this formula to find the area enclosed. Okay, so we find f prime of t is 3t to the second. G of t is just 2t minus t squared. Alpha is 0 and beta is 2. So our area is the definite integral from 0 to 2 of g of t, which is 2t minus t to the second, times f prime of t, 3t to the second, dt. Okay, so this is a pretty simple integral to evaluate. So we might as well go ahead and do it. Oh, we get 6t to the third minus 3t to the fourth and 6/4 t to the fourth minus 3/5 t to the fifth from 0 to 2. So 6/4 reduces to 3/2. So 3/2 times 2 to the fourth is 16. And then minus 3/5 times 2 to the fifth is 32. And then the other contributions are 0. So 2 goes into 16 8 times, so we get 3 times 8, or 24, minus 96/5. So 24 minus 19 and 1/5. So the area is 4 4/5, or if you want to write it as an improper fraction, 24/5. Square units, whatever the units happen to be. Okay, that's not too bad, but so the trick here is, read the directions carefully. If it's enclosed by the graph and the x-axis, then find the t-values where y is 0. Those will be the limits of the integration. Okay, the next part, arc length. From chapter 8, section 1, the length, capital L, of a curve C defined by y equals k of x for values of x between a and b is L equal to the definite integral of the square root of 1 plus k prime of x squared from a to b. Since y equals k of x, dy dx equals k prime of x, and the square of the derivative is k prime of x squared. We already knew that. So the arc length formula can also be written in Leibniz notation. So we saw all of this when we covered section 8.1. All right, but now we suppose that the curve C described above is traced once from left to right by parametric equations, x equals f of t and y equals g of t, for values of t between a and b, or alpha and beta, I mean. From left to right means that as t increases, x increases. And so that will mean that the derivative of x with respect to t is positive. Okay, then the arc length, in Leibniz notation, the definite integral of the square root of 1 plus dy dx squared from a to b, can be transformed to this definite integral. It's the square root of 1 plus. So here we're just plugging in what dy dx is. It's dy dt over dx dt squared, and then dx dt dt from alpha to beta. And this is equivalent to this simpler definite integral for the arc length. It's the definite integral of the square root of dx dt squared plus dy dt squared from alpha to beta. So that's a fairly simple formula to remember. You might remember that we did go into some detail when we first derived the arc length formula using this sort of idea. Okay, let's go ahead and find the arc length of this curve, defined parametrically. The parametric equations are x equals the square root of t and y equals t squared over 8 plus 1 over 4t for values of t between 1 and 9. Okay, so we need to know what dx dt is. So since x is the square root of t, dx dt is 1 over 2 times the square root of t. And the derivative of y with respect to t will be t over 4, and then minus 1 over 4t to the second. So let's go ahead and write dy dt as a single rational expression with a denominator of 4t to the second. So we'll get t to the third minus 1 over 4t to the second. We need to square each of those and then add them together and put them inside the square root. So why don't we do that in this step? Let's square dx dt, add it to the square of dy dt. Okay, so I'll do half of it. The square of dx dt is just 1 over 4t, and you do the other half. So what goes in the denominator when we square dy dt? So 16t to the fourth, that's what I get. And then when we square the numerator, square t to the third minus 1, we get t to the sixth minus 2t to the third plus 1. Okay, let's write this sum as a single rational expression with a common denominator. So if I multiply 1 over 4t by 1 in the form 4t to the third over 4t to the third, then we'll have a common denominator. So multiply 1 over 4t by 4t to the third over 4t to the third, and we get 4t to the third plus t to the sixth minus 2t to the third plus 1 all over 16t to the fourth. And we can simplify the numerator by combining like terms. So we get t to the sixth plus 2t to the third plus 1 over 16t to the fourth. And do you notice what we can do with the numerator? The numerator is a perfect square. If we square t to the third plus 1, we get t to the sixth plus 2t to the third plus 1. And the denominator is also a perfect square. If we square the term 4t to the second, we get 16t to the fourth. That observation is of interest because this is what goes inside the square root. So our area, we're not computing area, we're computing the length of a curve from t equals 1 to 9. I'll go ahead and write this all out to start with. We have the square root of all of this. But this is going to give us a pretty nice integral to evaluate. The square root of t to the third plus 1 squared is t to the third plus 1. And the square root of 4t to the second squared is 4t to the second. Since there's just one term in the denominator, we can write the integrand in separate terms. So t to the third over 4t to the second is just t over 4. And then plus 1 over 4t to the second, we can write that as 1/4 times t to the negative 2 if you like. So we're just a couple of steps away. Find an antiderivative. So we get t to the second over 8. And then minus 1 over 4t. Evaluate that from 1 to 9. So it looks like we're out of time, but we're almost done. 9 to the second is 81 over 8 minus 1 over 36. And then from that, we subtract the quantity 1/8 minus 1/4. So I'll leave the rest of that for you to do. Tomorrow we'll do the rest of section 10.2 and possibly start section 10.3.